I'm very happy to have the opportunity to share with you the problems I made during the automation phase of an enzymatic HTS assay. Don't worry, I will also give you the solution we found. My talk will be divided in 3 parts. The 2 first one will present you the 2 first strategy with classical dispense instrument, and in the third one, I will present you the last strategy based on the eco technology. In theory, this HTS project doesn't represent a major challenge. We had to identify inhibitors of the enzymatic activity. The protein was available in a large amount, so it was not limiting step in the assay development. And the assay was quite simple, based on the non-fluorescent substrate that generate fluorescence after cleavage by the enzyme. So we had to make 4 dispenses: the buffer to resuspend compounds in the assay-ready plate made by the compound management service, the enzyme, the substrate, and finally the stop solution. So after we set up the assay condition, we went for the automation phase, and in first intention, we decided to go for multi-drops and rapid stack for all dispense steps. This process was quite easy to implement. High throughput, we could easily screen more than 100 plates a day, and it didn't really need a precise scheduling, as all dispenses were made with the same robotic system. So came the time to screen the pre-screen library, and so this library is used to validate the robotic process, and it's a library that represents a part of the diversity of the full Servier's library. We screen the compounds at 10 micromolar in 2 independent experiments to see the robustness of the process. I will present you the result of the pre-screen using multi-drops and rapid stack in the next slide. So in this slide, I present you the monitoring of the control and the Z prime from this first pre-screen. So you got the 2 experiments, N1 and N2 on the same graphs, N1 on the left and N2 on the right, and both N has been made in 2 independent runs. On the top part, so you got the control, the basal signal, and the maximum inhibition signal. As you can see, there is some variability in the basal signal with an increase of the basal signal along the time, along the plates. If we look now at the Z prime value, there is more variable values than for the controls, with a very nice wave effect. So regarding these 2 parameters, control and Z prime, we could already suspect some problem in the process. So now if we look at the correlation between the 2 ends, we can easily see there is no correlation between N1 and N2. And even if some very potent compound seems to be correlates. We try to explain those results, and especially the absence of correlation. It appears that we had some strong problem with the substrate. We got some big problem of adsorption in the silicon tubic system, and also some problem of stability of the non-fluorescent form of the substrate that is able to cleave by itself. So, because we were quite short in time, we decided to change the automation system, and I will present in the coming slide the second strategy. So after the bad surprise with the multi-drop, we decided to use another liquid handler we've got in the lab, the Servier. In fact, we observed less adsorption of the substrate on the plastic tips than on the silicon tubing, even if the use of the Servier is decreasing a bit the throughput of the assay. In this case, we decide to dispense the substrate and the enzyme with the Servier. And I will present you the result of the pre-screen using these robots in the next slide. So, as you can see, there is a major improvement in the correlation and Z prime by plate, even if we can see some small variation in the Z prime. At the bottom part, you've got a graph that represents the median effect of the compound by plate. And as the compound have a random distribution in the plates, we should observe a similar median value of the compound effect by plate. And as you can see, there is no big difference between plates and between N. So definitely, we can see a major improvement of automatization of the assay. But it's improved, but it's not perfect, as we can see in the next slide. So now, if we look at the control monitoring results, it's definitely horrible. We observe a strong disruption in the level of the basal signal all along the run, and we were able to link those variations to the precipitation of the substrate in the reservoir of the CB well. Precipitation that was increased by the refill of the reservoir, as the reservoir was not big enough to have the volume for a full run. And as you can see on the bottom part of the slide, on this global overview of the plate, we've got a beautiful line effect on all plates. So if we look more precisely to this slide, we can see that there is a very beautiful and robust and repeatable line effect. We found that the stop compounds, different from the first process, was also adsorbing a lot to the silicon tubing. The use of the CB well doesn't solve our problem with the substrate, as precipitates, and the result was that only 15 micromolar of substrate was dispensed in the well in place of the 75 micromolar expected. So, in conclusion, CB well, and multidrop were not the solution for the automatization of our assay. I have to be honest with you, this project started to be a nightmare for me, with the problem of adsorption, solubility, stability, and precipitation. But by the time I was working or fighting with the automation, we installed in the lab a big robotic platform designed around an Echo 550. In fact, even if we were working for a long time at the compound management unit with the Echo to prepare the compound plate for the screening, we never had one on our own to play with for the assay development and the screening. So we decided we designed a big robotic platform named HIDE for High Efficiency Investigation Drug Instrument, and this platform has been designed around two echoes, one 550 and one 525. Originally, this platform has been designed for cellular assays in HTS and HCS, never for an enzymatic assay. This platform integrates a robot arm, two echoes, a BMG reader, washer, multidrop, centrifuge, pillar, sealer, two cytomat, and now a Yokogawa reader. So everything to perform cellular assay in HTS or HCS, but also to supply to help our colleague from the compound management unit. As we had now ID and the echoes in the lab, I proposed to our robot engineer to test the dispense of the substrate using the echo technology. So imagine his face when I proposed him to realize the screening on an integration that was for less than 2 weeks in the lab and without total validation of the robot and of the integration. But we tried. So we adapt a bit the design of the assay to integration. So the Echo 550 will be dispensing the substrate. The two multidrop combi will dispense enzymes and buffer for the refill. And as we've got a reader online, we removed the stop step that was part of the line in the second pre-screen. With this new design of the assay, we were able to run up to 60 plates a day. And I will present you now the result of the third pre-screen. For a robot that has been installed for less than 2 weeks, we were very happy about the result. Control at Z prime were quite stable, and definitely the Echo 550 was a major improvement in the process. As we were dispensing the stock solution of substrate without any tips, we expected having the right concentration of substrate in the well. And we didn't observe anymore the line effect. The compounds were stable, and we've got a good correlation between N1 and N2. So we gave the go for the screening regarding after these results. So Heidi ran her first screen as a big girl only 3 weeks after her installation. And you can see the result of this one-dose screening on this slide. On the top part, you can monitor the Z prime by plate, and on the bottom part, you've got the control values. And as you can see, there is more variability than expected. One of the reasons of this variability is the heat wave we've got in Paris at the time of the one-dose screening. Even if we try to keep the temperature as stable as possible in the lab, we observe some variation in the temperature between the morning and the afternoon, between 2 and 4 degrees during the day. And also, something we didn't anticipate was the increase of the temperature inside ID, due to the fact it's a totally closed structure because of the security. And if you look at the distribution of the compound's effect, we are far away from a Gaussian distribution. So it was definitely impossible to run classical campaign analysis. So it's why we decide to perform an analysis by plate. And also we accept to screen in dose response more compound than usual. And as you can see on this graph that show you the correlation between the PEC50 value of the compound between N1 and N2, it was a very good idea to use ID. We have a very good correlation between the two independent experiments with a correlation around 0.9. And you can't imagine how happy I was to see such a good correlation. The dispense of the substrate by the echo was a very good idea, and we obtained a very robust assay with a very weak variability between the technical replicates. In addition, to confirm the robustness and the quality of the result we obtained with the echo, 70% of the compound have been confirmed in an orthogonal assay, and 70% of the EC50 of this compound has also been confirmed. So with two different readouts, we validate 70% of compounds and also 70% of their EC50. So this project was the first one we ran on ID, and it was also the protocol we used to validate the integration system. Thank you very much to Xavier, our robotic engineer, to help me and especially to trust me. In the fact we were able to run a full HTS on the platform 3 weeks after its installation. So now the project is in a heat-to-lead phase. The main screen is the same as the HTS, using the Echo 550 to dispense the substrate. But now we have to integrate also 5 off targets in addition on the main targets. So we have to screen each week the set of compounds on the 6 different targets in parallel. Even if the assay is the same, we managed to keep the steps and to homogenize the incubation times. The substrate, or at least its concentration, are different between the enzymes, and definitely enzymes are not the same. But now we've got the second echo integrated on ID, the 525. And so we will integrate the 6 assays on the ID, and we are developing a protocol to run them on the same time in the same run for each replicate. We are going to use the 525 to dispense the protein and the 550 to dispense the substrates. We are expecting a gain in the robustness as we've got some purified enzymes that bind to the plastic, again adsorption problems. And also a gain of time and cost as running the 6 experiments, not in parallel, represent 4 working days for a technician. And we expect to reduce it to 1.5 days if we are able to run it in parallel on the ID. In conclusion, this assay was in theory easy to run, but classical dispensing instruments were not the solution. And I was maybe too optimistic at the beginning of the project regarding the automation. We've got some strong problem of adsorption, solubility, precipitation, and everything over you can imagine. ECHO has been the solution to this problem of adsorption and the robustness issues. And also, ID was the key to optimize the robotic process. Most important, ID and the ECHO technology arrived just in time in the lab to save the project and to avoid any more delays in the project. Also, ECHOs will be the way to screen efficiently the 6 targets on the same time for the hit-to-lead campaigns. From a general point of view, ECHOs are now in a central position in our assay development strategy and to prevent all the problem of adsorption for the proteins or the small molecules. Thank you very much for your attention.
Thanks, Céline. And now over to Ian.
Hi, good morning, everyone. Over approximately the next 10 minutes, I'm going to give you a brief introduction into LabSite as a company and go into a little bit more detail on the ECHO liquid handler product line and the underlying technology that drives it. LabSite was founded in 2000 and became the first company in the biotechnology field with the launch of the first ECHO liquid handler in 2004 to transfer liquids using sound energy. In 2011, LabSite launched a proprietary technology which we call dynamic fluid analysis. And this enables ECHO liquid handlers to automatically adjust to different fluid types. Perhaps more importantly, however, this has enabled the company to expand beyond the traditional drug discovery workflows. And working closely with customers, particularly in the genomics space, we launched the ECHO 525 in 2013, which could build larger volumes faster. And this has become the preferred system within the genomics applications where larger reaction volumes are required. To support the completely automated ECHO handler workflows, I also wanted to point out that we offer complementary automation systems that are easily tailored to support a wide variety of workflows out there. The ECHO liquid handler today now constitutes a family of instruments. On the left-hand side here, we have the ECHO 525. It is the instrument with the 25 nanoliter droplet. The two instruments on the right-hand side, in fact, have the 2.5 nanoliter increments and share all the same capabilities, with the exception that the ECHO 65XT, which was launched earlier this year in February, also accommodates a brand new acoustic sample tube, which was launched at the same time. Below this, I have the various consumables that are available to support the ECHO workflows, all the way from a reservoir up through a 1536 well format. Those come in both standard and low dead volume flavors, as well as with various coatings to support different workflows. And what is not shown on this particular slide, but I'm not going to go into any detail, is a wide variety of software that is designed specifically to support the workflows that our customers are interested in. At the heart of the ECHO liquid handler is an acoustic transducer, and that's depicted at the lower right-hand side of the slide. The acoustic transducer is responsible for generating the acoustic energy. It also serves the function of focusing that energy at the surface of the fluid being transferred. We have a coupling fluid that enables the acoustic energy to travel from the transducer into the particular fluid that we are transferring. And in doing so, we can generate droplets of either 2.5 nanoliters or 25 nanoliters and eject those from a source well up into an inverted destination well. For volumes that are greater than either the 2.5 or the 25 nanoliter, we're essentially just ejecting multiple droplets in succession. And those droplets can be ejected into either a dry well or a well that already contains some fluid in it. That ejection process is extremely rapid, so we can eject those droplets at rates anywhere between 200 to 500 droplets per second. We can also position that acoustic transducer under any of the wells of the source plate and position any destination well above the transducer. And so that enables us to do any well to any well transfer. As I mentioned earlier in my presentation, dynamic fluid analysis is proprietary to LabSite and has the unique benefit to the customer that it automatically adapts to fluid properties within the well and adjusts in real time as it's doing the transfer. It borrows from medical ultrasound as well as sonar. And if we view the video here, what you can see is that there is a low energy ping that's being emitted by the transducer. It's reflecting off three surfaces. First is the bottom of the plate, the second is the bottom of the well, and the third one is the surface of the fluid. And utilizing those reflections, we can infer two aspects to the fluid. The first one is the fill height of the fluid, and so that enables us to appropriately focus the acoustic energy on that meniscus. The second one is to understand the acoustic impedance of the fluid which is contained within the well. And that acoustic impedance basically describes how sound will travel through the liquid and enables the instrument to adjust to changing fluid properties as it moves from well to well. So what that means is that the instrument can accommodate a very wide range of fluid types, even within the same plate. And that could span anything from cell lysates to various reagents that are used in genomics or other applications. Those reagents could be at different concentrations. They could contain glycerol, surfactants. They could contain biomolecules such as DNA, RNA, or protein. So the advantages of the Echo liquid handler really fall into four major buckets here. The first one is maximizing that lab budget, and that's primarily through that miniaturization, but also the elimination of consumables such as tips. The second one is data quality, the ability of the instrument to very highly accurately transfer a predetermined volume and to do that very precisely. Is going to result in very consistent assay results time and time again. The speed at which the system is capable of transferring liquids, the ability to do any well to any well transfer, of course, translates into a very rapid assay design process. And then lastly, the need to automate complex workflows and the increased precision and accuracy that comes through that automation, as well as the ability to free up time for perhaps other higher value activities within the lab. I just want to give you a flavor for the extent of miniaturization that is possible with the Echo liquid handler. The examples that I'm showing here are from the genomics field, but I think they give you a perspective on what is feasible anywhere up to 100-fold. And of course, this is going to be direct savings in terms of reagents, but also if you are utilizing very precious samples, then that sample is just going to go that much farther for you. Okay, so just to quickly summarize, I mean, we've talked about the different flavors of Echo liquid handler that are available. All of those are ready to go out of the box and do not require expertise in robotics or liquid handling to make use of those. They all readily integrate into automation systems, both provided by LabSite or third parties. And I think what's important to take away with you is the transfer that you get with an Echo liquid handler is contact-free. And so that directly translates to higher data quality. There's no tips that are required for that transfer. It's highly flexible, so we have the ability to transfer from any well in the source plate to any well in the destination plate. And that enables rapid cherry picking types of applications to be performed. And it also allows steps potentially to be eliminated from your workflows. So because of the very low volumes that the Echo liquid handler is capable of working with, in many instances, pre-dilutions become unnecessary. And lastly, hopefully I convinced you that the Echo liquid handler has the potential to really help with assay miniaturization within the workflows that you're using.